I don't know why people call it a try. It's not a try. It's not a try. It's a tree. Just deal with the tree. CloudFlare's global network handles a lot of HTTP requests, over 60 million per second on average. That's at least one customer. I know you guys wouldn't understand, but that's minimally one customer, at least. That, in and of itself, is not news, but it is the starting point to an adventure that started a few months ago and ends with the announcement of the new open source Rust crate that we've been using to reduce our CPU utilization. That's Pingora, right? Is that Pingora? Enabling our CDN to handle even more of the world's ever-increasing web traffic. Pingora. Let's start at the beginning. You may recall a few months ago when we released Pingora at the heart of the Rust-based proxy services. I've always wanted to write some sort of a proxy. I've never written a proxy before or a reverse proxy. It's on my shit list of things I need to do, and so that's what we're doing. We're doing that. As an open source project on GitHub, I work on a team that maintains the Pingora framework as well as the CloudFlare's production services built on it. One of those services is responsible for the final step in transmitting a user's non-cached request to their true destination internally. We call the request destination server its origin. So our service has the unimaginative name of Pingora Origin. All right. One of the many responsibilities of Pingora Origin, by the way, non-clever naming. Beautiful. Can we all agree that non-clever naming is, in fact, the best way to go about not having stupid names? Okay, I really don't want Galacticus telling me about getting date times from the user. Is to ensure that when a request leaves our infrastructure, it has been cleaned to remove, the internal information we use to route, measure, and optimize traffic for our customers. This has to be done for every request that leaves Cloudflare. And as I mentioned above, it's a lot of requests. At the time of writing, the rate of requests leaving Pingora Origin globally is about 35 million requests per second. That is so many. What is 35 times 864? All right. So we're going to have to add a lot of zeros to this number, right? So this is 30,000, which becomes 3.02 millions. Is that a trillion? Are we trillion territory? They handle a trillion requests per day? No way. No, we're trillion territory, aren't we? No. A million millions is trillion, not a billion. You guys are doing bad math. It's not a milli, it's not a billy, it's a trilly. Okay, billies are at the 9. I can't even count that high. I know, they're like, nah, yeah. I love watching you guys do math. You make fun of me for doing math, and then I watch you guys do math, okay? Oh, you guys think it's easy. Oh, you guys think it's easy to use math. Well, guess what? All right, let's get back to this. By the way, that's a lot of traffic. That's crazy amount of traffic. Just adding and removing from a map 3 trillion times is an insane amount of compute. Think about all the other stuff that has to do. It's a trillion, not trillion. Yeah, exactly. Any code that has to be run per request is in the hottest of hot paths, and it's in this path that we find this code and comment. Perf, heavy function, 1.7% CPU time. Clear internal headers. Internal headers, iter, for each, remove them all from header. Oh, yeah. I mean, this makes sense. How else would you handle this? I'm very curious. This small, pleasantly readable function consumes more than 1.7% of Pingora Origin's total CPU time. To put that in perspective, the total CPU time consumed by Pingora Origin is 40,000 compute seconds per second. Every second they use a half of a day of computing. I don't really understand this. Are they saying that this one function or the entirety of it? Yeah, Cloudflare engineering is so interesting. Yeah, but their sales tactic repel me. What, you don't like their trust and safety team? You can think of this as 40,000 saturated CPU cores fully dedicated to running Pingora Origin. Of those 40,000, 1.7%, 680, are only dedicated to evaluating clear internal headers. That's so amazing. That is so amazing that you can effectively boil down this function to 680 cores running nonstop, fully pegged 100%, just clearing internal headers. The function's heavy usage and simplicity makes it seem like a great place to start optimizing. I bet you they could do this in such a more clever way. Hear me out. Cloudflare, hear me out. Every HTTP request you make, the first X headers for routing are all defined with a certain amount of space. Every single time. White space will just pad it out, and then you do the slashes that you need to do. You know why? because you can even make up like a fake header to fill in all the space. And then when you want to remove internal headers, instead of removing the headers on a header object, say a map, you literally just string slice that son of a bee clean out. Tell me that's not a good idea. No, like this. Okay, stonks. Yeah, we're straight stonking, boys. Boys, we're stonking. Okay, that's an idea. Okay, so every HTTP request looks something along the lines of this one, right? So it's like HTTP 1.1 / whatever, right? You have your basic header, and then you probably have something like method, that's post, get, or whatever. But instead of doing, and then you have all your other headers, right? They probably have a series of headers that look something like this: x-cloudflare some name, right? And then it has some value, and then you have a registered nurse. And then you do another X, Cloudflare, registered nurse. Now, let's pretend that on every single request, you just simply say, hey, we need, 2,048 bytes every single time. I don't know how many bytes you need. Maybe you can reduce it down to a whole bunch. When you want to strip the headers, instead of going through your actual header and doing all that, maybe you could fully format your request. And at the bytes level, right, at the very end of the pipeline, at the very end, all you do instead is just go bytes, 0 through some number, right? Maybe you could pass in this index because maybe you have, maybe this thing is not as clean as we're making it, all the way up to index plus your maximum size, and for the rest, right? Then you're only doing pointer arithmetic. Pointer arithmetic is pretty free, comparatively. Can we agree to that? Comparatively, pointer arithmetic is effectively free. A singular removal from a map is probably 100,000 times more expensive than pointer arithmetic, or some astronomical number that I don't even know. Maybe it's only 500 times more, but nonetheless, it is significantly more expensive. There you go, Cloudflare. I just gave you an amazing idea to further improve it. You stole my idea. I'm suing you. Probably cheaper than map lookup. It's probably it's gallons cheaper than a map lookup, because a map lookup, you got to remember, it computes a hash. It probably does a modulo, as all maps do, and then it has to do a linked list, a traversal, and then it has to do a key comparison, right? Like that's just going to be a lot more than X plus a number, right? Like this is vastly cheaper than that. Gallons are such a great freedom unit. Yeah, I use the most appropriate. No. You got that all wrong. That's not what /r/n stands for. Dude, what are you talking about? /r stands for registered. /n stands for nurse. It's a registered nurse. Everybody knows this. Like, everybody knows that. There's no carriage return. No. Okay, first off, what's a carriage? I didn't realize Cinderella's going to the ball right now, buddy. Carriage return? No. Registered nurse. This small and pleasant readable function consumes more than 1.7%. Oh, we already talked about this. Benchmarking. Benchmarking the function shown above is straightforward because we can use wonderful Criterion Rust Crate. Criterion provides an API for timing Rust code down to the nanosecond by aggregating multiple isolated executions. It also provides feedback on how performance improvements or regressions over time. I wonder if they do some sort of like, I don't know how Criterion works, but I'm curious if they just send stack traces every now and then to some sort of external service, because if you have this many requests, you could probably very easily visualize exactly what's happening through the entire ecosystem of Cloudflare and how fast or slow it is by just taking a single stack trace randomly throughout a user session every million requests, or probably every billion requests, considering they literally do trillions of them. And you could just have such a perfect. It uses eBPF actually. Okay, cool. I've never used eBPF. It also provides feedback on how performance improves or regresses over time. The input for the benchmark is a large set of synthesized requests with a random number of headers with a uniform distribution of internal versus non-internal headers. With our tooling and test data, we find that our origin clear internal headers function runs at an average of this much. Now, for each new method of clearing headers, we can measure against the same set of requests and get relative performance difference. Okay, nice. One potential quick win is to invent or invert how we find the headers that we need to remove from the request. And if you look at the original code, you can see that we are evaluating headers, remove header H. Yeah. For each header in our in our list of internal headers, we have okay, so for each header in our list of internal headers, so 100 plus times, diagrammically, it looks like this. Diagrammically, can you use the word diagram in a verb sense? Or is that an adverb? Can you use it adverbally? Is that a thing? I don't think so. All right. Internal headers, plus 100 in static vec, find and remove header request, this. Yeah. Since an average request has significantly fewer than 100 headers, 10 to 30, flipping the lookup direction would reduce the number of reads while yielding the same intersection. Because we are working in Rust and because retain does not exist for header map yet, we have to collect the identified internal headers in a separate step before removing them from the request. Conceptually, it looks like this. Nice. What they're already writing Pingora. They're already doing all of this. They could also just write a second. They could just write their own HTTP handling that allows for headers and just internal headers, right? Why not? And then to drop, you just go, no. He's right and that diagrammically is not a word, yeah. You're already writing everything else, so why not you could just write it in such a way that you just never actually do. No, it is, diagrammically, x.com, is this true? X, I want you guys to tell me. Am I even saying this word even remotely correct?
Diagrammatically.
I don't even know what you just said to me. Somehow that was not English. Just like, okay, bottle water boy. Bottle water boy. Nobody knows what the hell you just said. Using our benchmarking tool, we can measure the impact of this small change, and surprisingly, this is already a substantial improvement. The runtime improves from this much to that much. That's a 2.39x speed up or speed improvement for our function. Now remember, you could go all the way back up to here, and that reduces the CPU load by quite a bit. Remember also, they're doing something here that's a bit unfair to the problem themselves, which is saying that it's using 680 CPUs continuously and perfectly. You can't do that. So instead, this number also contains all the fluff metrics that are involved with it as well. So it's actually much higher than whatever this is. So saving that is already, that's great. Let's go. We can calculate the theoretical CPU percentage by multiplying the standard starting utilization by the ratio of new and old times. All right, nice. Unfortunately, if we subtract that from the original 1.71%, that only evaluates a savings of this, okay, or a 0.993% of total CPU time. We should be able to do better. Yeah, let's go. Let's do better because that's not even 1%. It's not even 1%. Searching the data structures. Now that we have reorganized our function to search a static set of internal headers instead of the actual request, we have the freedom to choose what data structure we store our header name in simply by changing the type of internal header set. Let's go. What do we got? All right, we got this one. To remove request headers, keys, filter map, get the keys, collect. Oh my gosh, you're doing it in that? Creating a vector. Oh, gosh. Heap allocations? Our first attempt used standard hash map, but there may be other data structures that better suit our needs. All computer science students were taught at some point that hash tables are great because they have a constant time asymptotic behavior or instantaneous lookup. It's not true. For reading, if you're not familiar with Big O notation, it is a way to express an algorithm consumes a resource. In this case, well, it's how it consumes a resource relative to its input. And so what this means is no matter how big you're dealing with in a hash map, it still has the exact same lookup time, whether it's small or whether it's big. Big L notation, more like that. And in this, in this case, time as the input side changes. Okay, I didn't finish that. This means no matter how large the map gets, reads always take the same amount of time. Too bad this is only partially true. In order to read from a hash table, you would have to compute the hash. Computing a hash for strings require reading every byte. So I've always been curious about this. I even think in my algorithms course I mentioned this, which is we have O of 1 lookup, but it can't be O of 1 lookup. It has to be O of key size lookup, correct? I've always been so dang curious about this. I think what they're saying is that I think the idea is that a map eventually could contain, tens of thousands of elements. And so this is the size they're considering. This size does not grow as input grows. I think that's what they're attempting to say. My girlfriend keeps telling me to practice the big O stuff. You don't have a girlfriend. Okay, I understand she goes to a school in Canada. I hear you, PHPP. So while read time for a hash map is constant over the table size, it's linear over key length. Wow. So our goal is to find a data structure that is better than O of L. Dude, big L coming in. O of L. Where the L is the key length, where L is the common Twitch chatter. Is that what we're about to hear? She goes to a different school, okay? I'll take. Hey, Wongad, thank you for the 10 gifted subs. Appreciate that. Plus ratio. Yeah, it's actually big OL plus ratio. There are a few common data structures that provide for reads that have read behavior that meets our criteria. Sorted sets like B-tree set use comparisons for searching that makes them logarithmic over key length, but they are also logarithmic in size too. The net effect is that even very fast sorted sets like FST work out to be a little 50 nanoseconds slower in our benchmarks than the standard hash map. A lot of times when you're getting really clever, you will find that these things don't make a huge amount of difference, right? Like a really funny thing is just storing stuff in an array. Like say you have 50 items and you store it in an array instead of a hash map, it's almost always faster to take an array and search through your array linearly than it is to put it into a map. Which is just hard for a lot of people to realize, but it's just sometimes being clever is not good. Sometimes being so stupid actually ends up being better. State machines like parsers and regex are another example, another common tool. By the way, CloudFlare has accidentally turned off the internet once due to a regex. So don't just use, just because they say regexes are a tool does not mean they actually are a tool. All right, they're an evil tool for searching strings, though it's hard to consider them a data structure. Yeah, I think internally our regexes push down automatas. I can't remember. My life is too far removed from the academic world. Are they push down automatas or are they not? I don't think they are. So if they're not push down automatons, then they're not a data structure. Are they or are they not? I can't remember. Anyways, regex can be a DFA. Okay, so they can be a DFA. These systems work by accepting input one unit at a time and determining on each step whether or not to keep evaluating. Being able to make these determinations at every step means state machines are very fast to identify negative cases. Yep, when a string is not valid or not a match. This is perfect for us because only 1 or 2 headers per request on average will be internal. In fact, benchmarking and implementation of clear internal headers using regex expressions clocks in as taking about twice as long as the hash map-based solution. This is impressively fast given that regexes, while powerful, aren't known for their raw speed. This approach feels promising. We just need something in between a data structure and a state machine. That's where a tree comes in. Don't just tree. A tree, pronounced like try, or tree. No, it's pronounced like tree, because it stands for retrieval, is a type of tree data structure normally used for prefix searches or autocomplete systems over a known set of strings. The structure of a tree lends itself to this because each node in the tree represents a substring of characters found in the initial set. The connections between the nodes represent the characters that can follow a prefix. Here's a small example of a tree built from the words and, ant, dad, do, and dot. So for those that don't know, it's just an autocomplete, right? It's just an autocomplete if you've never used an autocomplete. The maximum depth of a tree is the maximum amount of prefix characters that match. So if you have all of your words in there and the worst case is 4 matching characters, then the depth at max is 4. Or it'd technically be 5 because you'd have the actual leaf nodes that represent each word. It needs huge memory, though. Sometimes it needs huge memory. That's not necessarily true. Remember, clear internal headers have 100 headers. And my guess is that their headers, my real guess is that their headers probably all start with X-CF-. And so you could even drop those first in common 5 characters to reduce the size of your tree. That's my guess. And then you just start comparing headers starting at that. That's my guess. All right. The root node represents an empty string prefix, so the two lettered edges directed out of it are the only letters that can appear as the first letter in the list of the strings, A and D. Subsequent nodes have an increasingly longer prefix until the final valid words are reached. This layout should make it easy to see how a tree could be useful for quickly identifying strings that are not contained. Even at the root node, we can eliminate any strings that are presented that do not start with A or D. This paring down of the search space on every step gives reading from a tree the log of L we're looking for. Is it log of L? I wonder how they computed that. I think it's theoretically log of L, right? So when I say theoretically log of L, what it means is that theoretically you could have two words that have the same amount of characters all the way up until like the last one, right? You get a X dash, CF dash. This is the exact same prefix as the other one, X versus Y. And so that would be the only ones I think that could actually do that. But only for misses. Hits with the tree are still O of L, but that's okay. Well, again, it's sort of O of L, but because we're getting misses 90% of the time. Yeah, it's actually super clever that they did an inverse matching. So you use your tree instead of to match, you use it to inverse match. Brian being so serious while chat is in chaos is my favorite genre. I know you guys are absolutely insane. Right now, I'm watching TJ get just things deleted time and time again. It's just crazy. Mods get paid in exposure. Exactly. This is crazy, by the way. I'm actually trying to involve you guys. I'm really trying to involve you guys. But then you guys just turn into just absolute insane people, okay? Thank you. Thank you very much for the back-to-back subs. I appreciate that. If this mods get pinned, Prime needs to pay. Is mods livable? Of course, Nightshade, dude. You went from deleting his messages to pinning it real quick. All right, benchmarking a few tree implementations from Crates.io was disheartening. Remember, most trees are used in response to keyboard events, so optimizing them to run in both the hot path of tens of millions of requests per second is not a priority. The fastest existing implementation we found was Radix tree, but it still clocked in at a full microsecond slower than HashMap. The only thing left to do was write our own implementation of a tree that was optimized for our use case. Trie Hard, and we did. Today we are announcing Trie Hard. The repository gives a full description of how it works, but the big takeaway is that it gets speed from storing node relationships in bits of unsigned integers and keeps the entire tree in contiguous chunks of memory. In our benchmarks, we found that the Trie Hard reduces an average runtime for clear internal headers to under a microsecond. Nice. And we can use the same formula above to calculate the expected CPU utilization for Trie Hard to be this right here, 0.43%. That means we have finally achieved and surpassed our goal by reducing the compute utilization of Pingora origin by 1.71% minus this, 1.28%. 2 to the 7. It's beautiful. It's a power of 2. It's a power of 2. That is beautiful. Up until now, we have been working only in theory and local benchmarking. What really matters is whether our benchmarking reflects real-life behavior. Trie Hard has been running in production since July 2024, and over the course of this project, we have been collecting performance metrics from the running production of Pingora origin using a statistical sampling of its stack trace over time. Oh, nice. Statistics. Let's go. Statistic sampling of stack traces. Let's go. That's what Chrome uses, by the way, also. That's how Chrome determines how to improve JavaScript is by doing the exact same thing. Taking small little stack traces every now and then from just a couple users actually yields a really complete idea of what is being used and how often it's being used. You're not helping my dyslexia. He pronounces tree because it comes from retrieval. It does. It comes from retrieval. It's called a retrieval tree. Trie Hard has been running in production since July 2024, and over the course of this using this technique, the CPU utilization percentage of this function is estimated by the percent of samples in which the function appears, which is actually a really great way to do it if you have enough samples. If we compare the sample performance of the different versions of clear internal headers, we can see that the results from the performance sampling closely matches our benchmarks predicted. Nice. Let's go. That's really great. Actual CPU usage, oh, it went even down. Even better. Even better. Wow, nice. In conclusion, optimizing functions and writing new data structures is cool, but the real conclusion for this post is that knowing where your code is slow and by how much is more important than how you go about optimizing it. One would argue it's probably hand in hand, equally important. Take a moment to thank your observability team if you're lucky enough to have one, and make use of flame graphs or any other profiling and benchmarking tool you can. By the way, flame graphs, any proportional performance chart is truly the way to go. Because if you have a nice proportional performance chart, you can actually tell what is actually taking what time and by how much. No. 0.34 is better, right? Because it's the actual CPU usage. So someone said, isn't 0.34 worse than 0.43? No. Predicted CPU usage was right here. Actual CPU usage went down. So that means it's even better. Optimizing operations that are already measured in microseconds may seem a little silly, but these small improvements add up. You know what? I would personally say anytime you're doing performance work, it's fun to make things faster. It just is. It's a fun exercise, and even if you're making little bits faster, you are improving the experience, hopefully, for a lot of people. And for CloudFlare, every single little percentage actually makes a giant difference. So hopefully they continue to enjoy that. I mean, I really enjoyed this article. This was a fantastic article. Good job, Trie people. I hope you do try hard one day. I know it's called the Trie. You know what? Just for you, I will pronounce it the way you want me to. A good day to try hard, saving 1% at a time. Good job. The name is the 1%. The 1%. I gotta go pee. I do.